Okay then, I'm going to talk about an extension of a pretty well-known idea, or I'll call it extension for now. Fine. In physics, one thing that a popular question to ask kids about or to consider is, you have an object that's thrown in the direction of, here we go, some vector v0, and the question is, what angle should you throw at above the horizontal to maximize the horizontal distance traversed? So something like this. You know you're going to throw this object. It's going to follow that path. And the question is, how do we maximize this distance? Okay? That's our goal, our horizontal distance traversed. And you end up showing that 45 degrees is the optimal angle to do this. Alrighty. So what we're going to do today, and there's another video actually that explains that. But what I'm going to do today is I'm going to do a problem where we consider slightly different condition or different initial conditions. Consider this, right? So here's the vertical, and we're throwing downhill this time. Okay? So we're throwing downhill, again, in the direction of there's the direction we're going to throw in. And the question now is, if I'm going to throw at an angle of, say, beta with respect or above this slanted downhill direction, question is, what should beta be, or what relationship should exist so that we can maximize the distance before this ball makes contact down here? So now we want to maximize that distance. That's our goal. Okay, so let's go back to this problem for a minute. Okay, and back in this problem for a minute, because if we just remember how we do this, then when we go back to the other example, you'll see we're going to do a quick transformation and make it look like this problem. Alrighty, so let's just make sure we're clear about things. We're moving horizontally. We say we're moving in the I direction. Moving vertically, so we're moving in the J direction. And in this situation, the force that we're experiencing would be the acceleration due to gravity, which we could write like this. We can say that acceleration due to gravity, we want as a function of time, would equal negative g times the vector j. Okay, and that's the vector function that tells us the direction and of gravity, and then how much we're experiencing, in this case g. All right, so since we know that the derivative of velocity is acceleration, we take the antiderivative of this expression, and we'll get the following. We'll get negative g times t j plus the initial velocity vector, okay, which is just arbitrary, and here it is right there. That's the initial velocity vector. Okay, this is going to describe our velocity of our object as it moves, and then we can integrate again, and if we integrate again, we get the position function, which I'm going to call r of t, and r of t would equal negative a half gt squared j plus t times v0 plus some constant, which is usually the initial position. But in our case, the initial position, without loss of generality, I'm just going to designate it to be the origin. So there it is. So this is just equal to 0. Comment about going from here to here, just in case. Remember, we're taking the antiderivative with respect to t. So t is the variable. So that's why I added 1 to t's exponent and then multiplied by 1/2. All right, so let's give a little thought to that velocity vector. Okay, this v0 here for a minute. And then we're going to rewrite this expression in vector form with an I component and a j component. So v0, if we think about it, up here is the vector v0. It has a length, which I can denote norm of v0. Let's write that not like that. And once you consider the norm of this vector, you can then consider its two components, right? So this component here, right here, would be norm V0 cosine alpha, a little trigonometry in the triangle there, SOHCAHTOA, whatever you want to call it. And then over here, same thing, or similar, we'll get you this. Okay then. So now that we have that, that means we can write the vector V0. The vector V0 would be norm V0 cosine alpha I plus norm V0 sine alpha j. All right, so there we go. So now I'm going to take that expression and plug it in here. So R of t now is going to look like this. R of t is going to look like negative a half gt squared j plus t times, and instead of writing V0, I'm going to write that expression from here. So here we go. So if I do that, I'm going to get the norm of V0 cosine alpha I plus the norm of V0 sine alpha j. Okay, so then I can collect like components, and here's what I mean by that. If you look at it, this here, this is something as an I component, so it would not add to what's happening with this expression. But these two here are both in the same direction, so those vectors can be added. So let's write R of t one more time. So R of t is going to equal the norm of V0 times t cosine alpha I plus, and then we're going to have this expression. I'll write it this way. The norm of V0 times t sine alpha minus a half gt squared times j. Okay, so now we have an expression for R of t, and with a little bit of thought, we can figure out what we need to do to maximize the horizontal distance traversed. All right, so if we just think about our original picture here, okay, we can actually find the time it takes. There's a time over here it's going to take, t equals something, for this object to land on the ground again. And we can find that by thinking about the following fact. When this thing hits the ground again, the distance in the j direction would be 0. I should be careful. I wrote, this should be a j. I said j before, but I think I wrote I by mistake, obviously. All right. So what does that tell us? Well, we can take the j component and set it equal to 0 and find the times when the height is 0. So we take this thing and I set it equal to 0, I get the following expression. V0 t sine alpha minus a half gt squared equals 0. We can factor a t out. We factor a t out, then inside we have the norm of V0 sine alpha minus 1/2 g t equals 0. And the first term, well, the first factor gives me t equals 0. If you think about that, that's just over here. That's when this thing starts off before it's shot out at this in the direction of V0. And then the other time turns out to be t equals 2 norm V0 sine alpha over g. Okay. So there you go. And that second time would correspond to right here. And believe it or not, we're right at where we want it to be. Okay, our goal here was to maximize or figure out what angle would give me the maximum horizontal distance traversed. But I have an expression for the horizontal distance I've traversed. It's right here. It's this thing. So, because that's the distance in the x direction, because it's multiplied by the vector I. So what I can do is I could take that time I just found and plug it in here. All right, so if I do that, I get, well, let's just look at it. It's norm V0. And then instead of writing t here, I'm going to write this expression. So it's going to be times 2 norm V0 sine alpha over g. So that's where t was before. Let's be clear about that. And then let's not forget, it also gets multiplied by the cosine of alpha. Okay, so that's what you have. All right, so here we go. That's this is the relationship for the distance traveled. You can write it as x equals if you want, but it's our horizontal distance traveled. Now, if we look at this expression, we can figure a few things out. So first, I'm going to collect a couple of things. So I'm going to put v0, the norm of that squared, times 2 over. Actually, I'm going to leave the 2 away. I'll show you. You'll see. Make a decision here. And this is g, and then this is going to get multiplied by 2 sine alpha cosine alpha. And I just did this to be convenient because I look at this expression and I know something about it. It's actually a trig identity, and this expression equals the sine of 2 alpha times some coefficient here. All right, so what do I know about the v0? v0 is determined in the problem. I can't do anything with that. The acceleration due to gravity I can't change. But alpha is the thing I have the chance to vary, right? And the question is, what should alpha be to maximize horizontal distance? Well, if you think about this expression, the following thing is true. The sine of any angle, 2 alpha, whatever it is, the greatest that could ever be is 1, and the least it could ever be is -1. Okay? Well, if I want this thing to be as big as possible, I want this whole expression to be as large as possible, then I need the sine of 2 alpha to be as large as possible. And the sine of 2 alpha, the biggest that could ever be is 1. So if I want the sine of 2 alpha to equal 1, then that means I need 2 alpha to equal 90 degrees, because the sine of 90 degrees is 1. And then therefore alpha equals 45. The famous 45 that we always know. Okay, so we did all that, and then let's not lose track of what our goal is. Our goal is actually to try and do something similar for this problem. Okay? Now we're throwing an object, and we're throwing down a hill, and the question is, how do we maximize this distance, d, now? All right, so to do that, we need to, or I'm going to suggest that we rewrite or draw this picture in a slightly different way. See, I really like all this math I just did. It was easy to do and work out and so forth. It was nice that the distance that we're interested in being 0 again, like right here was 0 right there and there. So I'd like to get something where I had a horizontal line in it. So actually, that's exactly what I plan to do. I'm actually going to take this picture and rotate it a little bit. Now I'm just going to label a few more things. I'm going to call this whole angle here alpha. And then the question becomes, what's a good amount to rotate this whole picture by so that this piece along the bottom here becomes horizontal? Okay? So a little bit of thought, we can do that. All right, so let's just think about this for a second. If I draw a line out like that in such a way that this is a right angle, then you actually know that angle in there, right? According to the way I've labeled things, that's going to be alpha minus 90 degrees, right? Because that's 90 there, and alpha includes that plus this little piece here on the bottom. So alpha minus 90. Okay, so I'll draw one more thing here, and then we'll be set. You think about a horizontal line down here parallel to this horizontal line, then you remember from alternate interior angles, right? So here's alternate interior angles. You have this acting like a parallel line, here's a parallel line, and then this thing here is acting like the transversal. So that angle in there is also alpha minus 90 degrees. And that is how we're going to rotate our picture. Okay? So if we do this, here's what it ends up looking like. End up getting the following. Here's your horizontal line. Now, what used to be the vertical is rotated. That's going to matter a lot in a minute here. And there's alpha. And then somewhere in here, this is beta. Okay, here's the vector v0. Here's the path of our object. Okay. All right, now there's one thing we've got to be careful of. Because we've rotated this whole picture, we've actually also rotated the force of gravity. remember, this is the real picture. So gravity is moving in this direction. That's F sub g. All right? So now gravity is moving in this direction, parallel to this line, which used to represent vertical. All right, so we need to re-express our gravity vector. So here we go. So A, gravity, is going to be the following. Now let's think about this for a second. Our gravity is going in this direction, so it has a component here and a component here. Okay, and here's that angle. That's the angle alpha minus 90. Okay, and this is G. So the gravity vector now has components. So we'll call this F sub G, or acceleration really in our case. And let's think about its components. Here's one of them, and here's the other. Okay, let's call this, well, for the time being, just to simplify things, I'm going to say G is the length of that rather than norm G. I'm just going to do that for the rest of my calculations. Okay. All right, so if we do that, then we end up with the following. So just some trig again in this triangle. So here we have opposite over hypotenuse. So you're going to have G times the sine of alpha minus 90 times I minus G times the cosine of alpha minus 90 times J. Okay, and that's coming, here it is. There is this piece right here is G cosine of alpha minus 90. And then across from that, alpha minus 90, here's the G sine of alpha minus 90. Okay, so now we can actually simplify these things a little bit because there's some identities for expressions like this. Okay, so here's two identities. The sine of A minus B is equal to the sine of A cosine of B plus the cosine of A sine of B. And then you also have, for that expression over here, the cosine of A minus B is equal to the cosine of A cosine of B plus the sine of A sine of B. It comes from trigonometry. Okay, so we can apply those and then rewrite this expression. So for example, the sine of alpha minus 90, if we follow that first rule, it's going to give us the sine of alpha, the cosine of 90, plus the cosine of alpha sine of 90. All right, but cosine of 90, that little piece there is 0. So this whole term goes away, and we just end up with what's left. And then the sine of 90 is equal to 1. So this just turns out to be, hold on a second here. That should be minus and minus. Sorry if you noticed that earlier and I didn't say anything. All right, so this turns out to be negative cosine alpha. All right, this one's correct though. Cosines never match there. Okay, so for the other piece, we're going to have the cosine of alpha minus 90, and that's going to equal the cosine of alpha cosine of 90 plus the sine of alpha sine of 90. So when that's all said and done, you get just the sine of alpha. All right, so now we're actually ready to rewrite our acceleration function. Our acceleration function can look like this, a little more compact than it was before. So it's going to be negative G cosine alpha I minus G sine alpha J. And that's just coming from this thing up here. What I've done is I've replaced this expression and this expression with the things that we found out down here, this and this. Okay, so there we are. Now we're going to follow. It's going to feel familiar. Go back to the other problem. If you remember, we started with an acceleration vector, and we took an antiderivative to get a velocity vector. So we'll do the same thing here, actually. So here we go. So we get v is equal to, and we get negative gt cosine alpha. I'm going to use a little vector notation now. I want to be careful. So this way, when I write this, that means a vector. When I write this, this means the norm of that vector. So we'll stick to that convention for the rest of the time here. All right, so we have this. I plus negative gt sine alpha j plus some initial velocity vector. Okay. So, right, just keep in mind that this thing here is the vector vector v, or v0 really. And that's coming from this picture up here. That's my initial, that blue vector is my initial condition. Okay. So, moving right along. I'm going to be a little bit careful here about v0. We need to take a minute to write that. Because v0, we can actually do that. If we go back up to our picture here, here it is, right? We can draw its components. Here is horizontal component, and here's its vertical component. So its horizontal component would be the following. This is the vector v, so just v0 cosine beta, and this is going to be v0 sine of beta. So the vector v0 is going to equal v0 cosine beta I plus v0 sine beta j. That's what it's going to be. All right. So moving right along, we know that we have that vector now. This is v0 cosine beta plus I should say, plus v0 sine of beta j. All right. So then our velocity vector in total is going to be the sum of this vector plus that vector, which I just expressed here. So we get something that may not be so pleasant to look at. Let's see. Negative a half gt squared cosine alpha. Oh, no, hold on. I'm going ahead of myself here. It's negative gt cosine alpha plus v0 cosine beta I plus negative gt sine alpha plus v0 sine beta j. All right, good. So one more antiderivative and we're going to be there. We'll be at our position function. So let's do that. We'll call this vector r. And this is going to be, so now we're integrating with respect to t, so keep that in mind. T is our variable here. So here it is, that's a t. These guys are constants with respect to t. So here we go. Negative a half gt squared cosine alpha plus v0t cosine beta I plus negative a half gt squared sine alpha plus v0t sine beta j plus some r0, some initial vector. Now, just like I did in the previous problem, I'm going to designate this corner to be 0, 0. So that makes our initial position, the vector 0, 0. So we don't have to worry about that. So this thing here now is our expression for r. So now we're going to use the same reasoning we used in the previous problem, right? If this object is going to fly through the air, here's v0, and it's going to go like this, hit the ground again somewhere, then this is what I was really hoping for. I know that there's a time t equals 0 where this thing is sort of starting on the ground, and there's some time over here where it hits the ground again. Well, it's going to hit the ground again when the j component, this thing, equals 0. So we're going to solve for that thing equal to 0. And if we do that, let's write it out. So we get negative a half gt squared sine alpha plus v0t sine beta is equal to 0. That's what we want. And we'd like to solve this for t. Well, you can see that we can factor out a t here. And then you're going to have negative a half gt sine alpha plus v0 sine beta equals 0. So there's t equals 0 like we expected. And then over here, if you solve this, you're going to get t equals 2 v0 sine beta over g sine alpha. Okay, so we're ready now. Now what we're going to do is, this is the time it takes for the object to hit the ground the second time. That's going to be the time it takes to traverse this distance. So now we know that. All we want to do now is figure out what this distance is. And so to do that, we're going to take this expression, and we're going to sub it into the I component of r. The I component of r, because this is telling me my horizontal distance traversed. So this t here and this t here are going to be replaced with this value of t that we have. So you would get negative a half g 2v0 sine beta over g sine alpha squared cosine alpha plus v0 times 2v0 sine beta over g sine alpha times the cosine of beta. And now it's just a little bit of an algebra trip coming up. So here we go. So what do we have now? We know that we would have, let's do a little simplifying here. This expression will become negative 4 v0 squared sine squared beta cosine alpha over g sine squared alpha, plus over here we're going to have 2v0 squared sine of beta cosine of beta over g sine alpha. Alrighty. So now let's look for some constants here to factor out. If you're going to factor out, we think about what we're trying to maximize with respect to. We care about what beta we should use to maximize the distance down the hill. So I'm saying that because this expression has alphas and betas in it, and what we really care about is letting beta change. Alpha, if you think about it, is not going to change in this picture because alpha is this angle here. It's that entire angle, and that's going to stay constant. But beta is the thing we have some options about. We can go in that angle or that angle. All of these are different values of beta. So I'm going to factor out the things that are constant with respect to beta. If we do that, we end up with 2v0 squared over g sine alpha. And what's left is negative 2 sine squared beta cosine alpha over sine alpha plus, and over here you're going to have sine beta cosine beta. All right, time for another algebraic realization. This thing here looks a little bit like the sine of 2 beta. The problem is the sine of 2 beta would equal 2 sine beta cosine beta. So that means that this expression here would equal 1/2 sine of 2 beta. That's what that's going to be. Okay, so we're getting there. Let's go back to what we have here. So since this is a constant, let's just worry about this expression for the time being. All right, so I'm going to take this and rewrite it a little bit more. What can we say? I'm going to move some stuff around. So this is going to be negative 2 cosine alpha, and then over sine alpha. And then here I'm going to have sine squared beta plus 1/2 sine of 2 beta. Okay. So now let's keep our goal in mind. Let's just give this a name. I'm going to call it R, capital R, doesn't matter. I want to maximize this with respect to b. So what I can do is I can take the derivative with respect to b and set it equal to 0. So if we do that, here's what happens. The derivative of this thing right here turns out to be negative 2 sine beta to the first times cosine of beta Okay, that comes from just this part. And it's going to get multiplied by negative cosine alpha sine alpha. That's acting like your coefficient there. And then over here, I take the derivative. There's a chain rule. So it's going to be 1/2 cosine 2 beta times 2. All right, so let's do a little simplification here. Here the 2's cancel. So this will just become plus the cosine of 2 beta. Okay. And then over here, this is that sine 2 beta again, right? So it's negative sine 2 beta times this expression, the negative. I have an extra negative here, but be careful. This negative wasn't there. I wrote that for some reason. That negative is over here. Okay, so this would be positive. And then this turns out to be times negative cosine alpha sine alpha. Okay, now let's keep in mind we want this to equal 0 because we're trying to find a maximum. And we're ready. Here we go. All right, so move this term over. So we're going to have cosine of 2 beta equals positive sine 2 beta cosine alpha sine alpha, because I move this term over, it becomes a positive term. And then we divide both sides by the sine of 2 beta. So the cosine of 2 beta over the sine of 2 beta is equal to the cosine of alpha times the sine of alpha, or over the sine of alpha. And there you go. This is the condition that has to be satisfied to maximize that distance down the hill. And if you think about it, that really implies that 2 beta has to equal alpha, or that beta equals 1/2 of alpha. So in our picture, what that corresponds to, the original picture, here it is. We're throwing down the hill. Here's the vector v0. Okay, there's the angle beta. And here's the angle alpha. So what we're saying is if you want to maximize the distance that this object's going to travel down the hill, then beta should be 1/2 of alpha. And also, it's sort of interesting that does not contradict what we already know in the famous problem we always study. Here it is, in the 90-degree angle. Think about it. Alpha in that case is equal to 90 degrees. And every time we solve this, we always find out that beta is 45 degrees.